Hello again, everyone. We're continuing this series on how to build a drone tracking radar. In the last two videos, we explored frequency modulated waveforms and we saw how we could detect range. But there was a lot of clutter in those plots, and that clutter can make it hard to isolate real targets. So we need to figure out what is clutter versus what is a real target. But the problem is that these radar returns can vary wildly with different conditions, range, and movement. So we usually can't just set a constant amplitude threshold to detect targets. So CFAR, which stands for Constant False Alarm Rate, gives us an adaptive method to distinguish targets from clutter. It does this by setting a signal level threshold, which is calculated based on nearby range bins. But before we get too far into that, I want to say a special thanks to Marshall Bruner. A lot of the work that I'm using here came from his master's thesis at Colorado State University, and then we worked together to implement it on this phaser radar platform. Okay, so this CFAR technique is very popular and very widely used today. There's actually several different types of CFAR algorithms, but let's just focus on one called cell averaging CFAR. So cell averaging is going to be like taking a running average across all of our range bins. The basic steps for this algorithm are acquire the data and process the FFT, pick one of those FFT range bins as your cell of interest, then move some number of cells away, we call those the guard cells. Then average some number of cells, we call those the reference cells. Then multiply that average by some bias, and that will give us a threshold. Then we compare that threshold to the cell of interest. And if the cell of interest is above the threshold, then there is probably a target in that range bin. So let me distill all that down into 3 steps. Step 1 is to look at a range bin and compute the average around it. Step 2 is to offset that average by some amount. That is our threshold level, and you can see it as the red line. And then step 3 is we just delete everything that is below that threshold. So what is left over are all of the potential real targets and hopefully not very much clutter. So this gives us far fewer signals to have to think about and process than what we started with. And we can modify our FMCW program from last week to do all of this. This is the Python function that we need to add. It's essentially just taking a running average around some bin in our FFTs, and then we mask out all the values in the FFT that fall below that threshold. And of course, this is up on my GitHub page. Okay, so let's take a look at this in action now. So here's our waterfall plot, and I'm using the chirp synchronization that we talked about in the last video. And so this plot should pretty much look the same as that video. But this time, I'm going to keep the waterfall levels at their extremes. In the past videos, I used the waterfall levels to mask out everything except the highest peak. That's kind of cheating, so we're not going to do that anymore. Instead, we'll apply the CFAR clutter suppression algorithm and see if we can use only that to highlight just the moving target. And here's what that threshold looks like. You can see it as the red line. Right now, it just roughly duplicates the yellow FFT plot. And that is because our bias, guard, and reference values are all set at their minimum values. But if I increase the bias level, you can see how that red threshold line moves away from the FFT. Next, I can change the number of guard cells, and this is setting how many FFT bins do I want to skip before I start applying a threshold. So this is basically setting how big of a target do I want to detect. A small target would occupy just a few range bins, while a large target like an airplane or a building may occupy many bins. So for something like that, I would make my number of guard cells much larger. And then finally, the number of reference cells. This is the number of cells beyond the guard cells that will be averaged together to set the threshold. So if I make this value very, very large, then we just get a line that follows the average signal strength versus distance. But what we want to do is find some optimal combination of these 3 variables such that only our target peaks above that red threshold line. And then after we've set those values, we can apply those values here. So now the program is deleting all range bins whose amplitude falls below that threshold. And you can see that that really does clean up the plot quite a bit. And of course, we can tweak those values a bit further as needed. And again, here's what it looks like if I turn off the CFAR thresholds. Okay, so hopefully that made sense and was interesting. And with that, we're finally ready to put it all together into a complete radar. So that's what we'll do in the next video. I'll set this radar up outside and we'll use it to track the distance and velocity of a small drone. In that video, I'll also cover multi-chirp FMCW, I'll cover two-dimensional Fourier transforms, and range Doppler plotting as well. If that sounds interesting, be sure to subscribe and you'll be notified when that video posts. Thanks again for watching.